The last topic we'll talk about for chapter 6 is about periodicity, parts of the periodic table, and how it relates to the atoms. So we'll start off with relative atomic radius. This is going to be counterintuitive, but the hydrogen atom is actually bigger, not more massive, but bigger, taking up more space, being more voluminous than the helium atom. So let's talk about that for a sec. We've got 1s1 and 1s2. So the hydrogen atom has 1 electron and the helium atom has 2 electrons. Okay, so double the electrons. Let's talk about protons. We have 1 proton here and we have 2 protons here. So what do protons do to electrons? They attract them. They're attracted to each other. So the helium atom has twice as much attraction to its electrons than the hydrogen atom does. So the nucleus can pull twice as hard. And the other important part about this is, where did that electron go? So in my hydrogen atom, if I have my hydrogen nucleus here with its 1 proton, here's my electron. That's the 1s sublevel. Okay, what about my helium? 2 protons. It has both of its electrons in the 1s sublevel. So I placed the electrons the same distance away from the nucleus, and then I made the nucleus twice as powerful. So because the nucleus got twice as powerful, but the electrons were placed in the same position, they got pulled in, which makes that nucleus smaller. So the atom smaller. So this guy has their relative size is 31 to 53, and these are in nanometers. Yeah. Okay, so well, what happens with the lithium? It gets much bigger. I go from 31 to 167. I think it's obvious why the hydrogen is smaller than the lithium. It's got 3 electrons, and so it's considerably larger. But let's show its position around the table or around the atom. So we'll do P, P, P. So there's my lithium, 3 protons. Here its first 2 electrons, but its 3rd electron is in so this is the 1s, and this is the 2s sublevel. So that 3rd electron had to be placed further away from the nucleus because the inside energy level, 1s, was full. So I had to put it further away, which is why the lithium is significantly larger. Even though it's got 3 protons in it, those 3 protons are not powerful enough to pull that electron that's placed further away from the nucleus in that 2s sublevel. But what happens when I move over to beryllium? So beryllium has 1, 2, 3, 4 protons. Its first, oops, let me undo that. I'll erase this. Its first 2 electrons are in the same place they always are, in the 1s. Its next 2 electrons are in the 2s. So 1s, 2s. Okay. So it's in the 2s. So it was placed the same distance away from the last electron for the lithium atom, but the nucleus got 25% more powerful. So this got tugged in, which is why I go from 167 to 112. So as I move across the periodic table, the atoms get smaller and smaller and smaller because I keep putting electrons in the same energy level, which is the same distance from the nucleus, but the nucleus keeps tugging them in more and more and more, more and more and more, because it becomes more and more powerful. But then every time I fill up, so this is a full number 2 energy level, now I've got an over on this side, it's unfull. And so I've placed an electron further away from the nucleus when I move on to sodium. So each time I go from the right side of the table to the next bigger atom on the left side of the table, it gets bigger. And then I go across the table and everything gets smaller. And then it gets bigger. And then everything gets smaller. That's it. That's it for atomic radius. You can find those numbers on your periodic table. Ionization energy is the amount of energy needed to ionize an atom. So in this case, basically kick an electron off. The ionization energy follows this pattern. It takes more energy to go for any atom that's higher, and it takes more energy for any atom across the periodic table. So helium has the largest ionization energy, meaning if you're trying to take an electron away from helium, you better bring a lot of energy with you. Francium down here has the smallest, which means francium would actually like to give that electron away, and it doesn't take very much energy at all to get rid of that electron. It is very far away from the nucleus. So that francium's electron is so far away from the nucleus, it's as if we were going to lose a planet in the solar system, which planet will we lose? It wouldn't be Mercury. The sun's too close to that. It's going to be Pluto. Pluto is very far away. Gravitational pull on it is very weak. So the nucleus of the francium atom doesn't have very much pulling power on an electron that's 7 energy levels away. Plus, there are 60 or 86 electrons in between the last electron and the nucleus, kind of blocking the positiveness of the nucleus. And as I go up, it takes a little bit more energy because now cesium's 55th electron is much closer to the nucleus than francium's 87th electron. And I get smaller down to rubidium. Now it's only electron number 37. It's 2 energy levels closer to the nucleus than the francium was. Potassium is another energy level closer. Sodium, another energy level closer. I'm getting closer and closer to the nucleus, so the nucleus has a better hold on those things. It doesn't have a good hold on them, but it has a better hold on something below it. But then as I move across the periodic table, what's happening? I'm increasing protons. So as I'm increasing protons, the nucleus becomes more powerful. So the nucleus is pulling harder on those electrons as I add more positiveness to it. And the other part about that is, remember, as I move across the periodic table, I keep putting the electrons the same distance away from the nucleus, and they get tugged in more and more and more. As I jump to the next row, now I place them on the next shelf, in the next shell, in the next energy level. So it's hardest to get an electron away from helium, and it's easiest to get an electron away from francium. And if you're wondering about relative energies, whichever one is closer to helium, if I pick, say, this atom and say this atom, this one is closer to helium, so it's going to be harder to pull an electron away from the silicon than it is to pull one away from the indium. This one's indium. Okay. And then the next thing is about electronegativity. Electronegativity is the ability of the atom to take an electron from something else. So the numbers that we're looking for electronegativity are on the backside of your periodic table. They're green. The number itself is green. It's in the sort of the bottom right-hand corner. And if you look at, say, fluorine, it says 3.9. Oxygen says 3.5. Helium says 2.2. Carbon says 2.55. So this is the ability, the relative ability of an atom to pull electrons to itself. So francium is the best. And then the worst one actually is going to be helium. It doesn't even have a number. But of the ones that are not noble gases, the worst one is going to be francium. It's at 0.7. And that makes sense because it doesn't want to hold on to the electron that it has. So its ability to get that electron back or to grab an electron from somebody else is almost non-existent. Interestingly, for us at least, these numbers were created by Linus Pauling. Linus Pauling, he grew up in Condon, Oregon, which is east of the Dallas campus. His dad was the pharmacist. Condon is a super small town, but anyway, he's the only person to win 2 Nobel Prizes by himself. There are other people with their names on more than 1 Nobel Prize, but he has a Nobel Prize for chemistry and he has a Nobel Prize for peace. So only person with 2, and he's from basically here. Okay, so if I want to think about atoms as far as like their ability to take stuff away, so maybe think about them as a bully. Fluorine is the biggest bully on the periodic table for taking electrons away. And francium is the weakest of the atoms. It will give the electron to anybody who wants it. The noble gases don't want them, so it doesn't matter about those guys. But for the rest of them, they have a certain amount of pull, and depending on which atom they are, they have their poles are relatively seated in their positions on the table. For the most part, whichever atom is closer to fluorine, that atom is going to be able to take electrons away. And if they're equal distances, then the smaller atom wins. So my example of that is oxygen and chlorine. They're both 1 block away from fluorine, but chlorine is bigger. So its number is 3.16 and oxygen's is 3.5. So if oxygen and chlorine formed a compound with each other, oxygen would be taking the electrons away from chlorine. If nitrogen and chlorine formed a compound, now nitrogen is 2 blocks away from fluorine and chlorine is only 1 block away. So chlorine would be taking the electrons away from nitrogen. That's how that works. Okay, so this is it for this. Oh, no, sorry, Lewis dot structures. The last thing is something pretty simple. Lewis dot structures are something that were created by Jean Lewis. He was a chemist a long time ago, and he came up with Lewis dot structures. He's got a couple of things in chemistry named after him, Lewis acids and bases. But this one is super easy. So what he did was he literally just put a dot or multiple dots next to an atom, and that told the person that they were looking at which atoms or electrons were going to react. So since chemistry is all about actions of electrons, what Lewis is saying is there's 1 electron that's going to be reacting with sodium. Sodium has 11 electrons, but only 1 of them reacts, the final electron, the 11th electron. The other 10 are off limits. So fluorine, same kind of situation. Fluorine has 9 electrons, but 2 of them are off limits, and the other 7 will do chemistry. The other 7 will chemically react. And so that's why there are 7 dots around the fluorine. For the most part, people put dots in pairs around the electrons because of orbitals, put 2 electrons per orbital. But how do I know how many dots to put on? Well, it's super easy. You just look on the table. We're going to skip over the transition metals, the D block. So column number 1 gets 1 dot. Column number 2 gets 2 dots. Column number 3A or 13, the boron column, gets 3 dots. Carbon gets 4. Carbon's column gets 4 dots. Nitrogen's column gets 5 dots. Oxygen gets 6. Fluorine gets 7. And the noble gas column gets 8, except for helium, which gets 2. And when you're at 8, you're full. That's it. It's not going to do anything. Except for fluorine, it only needs, helium, it only needs the 2. So yeah, that's about it. Alrighty, that's it for information from chapter 6.